Hello, 1, 2, 2, 2. Hello, guys, and welcome back to the channel, and welcome to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. Welcome to day 72. We are absolutely over 70% out of the whole learning journey on the DataCamp class, which is the data analyst in Python career track. We're starting a new course today, which is the 11th, which is the 12th course. We are looking at sampling in Python, and sampling is one of the cornerstone of inference statistics and hypothesis testing in Python. It's a powerful skill used in survey analysis and experimental design to draw conclusions without surveying an entire population. So the first chapter is all about introduction to what sampling is in Python. So we're going to be looking at what sampling is and why it is so powerful. We also learn about problem caused by convenience sampling and the difference between true randomness and few pseudo randomness. So without further ado, let's jump back to learning, and welcome to Introduction to Sampling in Python, and welcome to day 72 day of learning. So we have 4 chapters to cover in this course today. So I look forward to seeing you when we complete the whole lesson. So after this sampling in Python, we now have hypothesis testing in Python. After we complete these 4 chapters of sampling in Python, we're going to move to hypothesis testing in Python, and that is the last course. Then we're going to work on one more final project for this lesson. So let's get back to learning. I'll just share my screen real quick.
Hi, welcome to the course. I'm James, and I'll be your host as we delve into the world of sampling data with Python. To start, let's look at what sampling is and why it might be useful. Let's consider the problem of counting how many people live in France. The standard approach is to take a census. This means contacting every household and asking how many people live there. Since there are millions of people in France, this is a really expensive process. Even with modern data collection technology, most countries will only conduct a census every 5 or 10 years due to the cost. In 1786, Pierre-Simon Laplace realised you could estimate the population with less effort. Rather than asking every household who lived there, he asked a small number of households and used statistics to estimate the number of people in the whole population. This technique of working with a subset of the whole population is called sampling. 2 definitions are important for this course. The population is the complete set of data that we are interested in. The previous example involved the literal population of France, but in statistics, it doesn't have to refer to people. One thing to bear in mind is that there is usually no equivalent of the census, so typically, we won't know what the whole population is like. More on this in a moment. The sample is the subset of data that we are working with. Here's a dataset of professional ratings of coffees. Each row corresponds to one coffee, and there are 1,338 rows in the dataset. The coffee is given a score from 0 to 100, which is stored in the total cut points column. Other columns contain contextual information, like the variety and country of origin, and scores between 0 and 10 for attributes of the coffee, such as aroma and body. These scores are averaged across all the reviewers for that particular coffee. It doesn't contain every coffee in the world, so we don't know exactly what the population of coffees is. However, there are enough here that we can think of it as our population of interest. Let's consider the relationship between cut points and flavour by selecting those 2 columns. This dataset contains all 1,338 rows from the original dataset. The pandas.sample method returns a random subset of rows. Setting n to 10 means 10 random rows are returned. By default, rows from the original dataset can't appear in the sample dataset multiple times, so we are guaranteed to have 10 unique rows in our sample. The dot sample method also works on pandas series. Here, using square bracket subsetting retrieves the total cut points column as a series. And the n argument specifies how many random values to return. A population parameter is a calculation made on the population dataset. We aren't limited to counting values either. Here, we calculate the mean of the cut points using NumPy. By contrast, a point estimate, or sample statistic, is a calculation based on the sample dataset. Here, the mean of the total cut points is calculated on the sample. Notice that the means are very similar, but not identical. Working with pandas can be easier than working with NumPy. These mean calculations can be performed using the .mean pandas method. Let's start sampling.
Okay, so let's start sampling and exploring what sampling statistics is. We understand that a subset of the population is called sampling. When you're working with a subset of the population, that is called sampling. So I'll just go ahead and create a new Jupyter file notebook for this. I'll call it Introduction to Sampling in Python. Let's do that real quick. This intro to sampling in Python. Python. So let's just import. This was the file for our last analysis on analyzing crimes in Los Angeles. We just import all these libraries that we make use of. Okay, so now let's move on. So this question says, sampling is an important technique in your statistical arsenal. It isn't always appropriate though. You need to know when to use it and when to work with your data set. Which of the following is not a good scenario to use sampling? Okay, which of the following is not a good scenario to use sampling? So sampling has to be used when it is appropriate. So you need to know when to use it, either to use sampling method or to use the whole data set. You've been handed 1 terabyte of data about error logs for your company's device. 1 terabyte. Ooh. You wish to learn about the travel habits of all Pakistan adult citizens. You've finished collecting data on a small study of wing measurements for 10 butterflies. You are working to predict customer turnover on a big data project for your marketing firm. Which of this is not a good scenario to use sampling? 1 terabyte of data. That is a whole lot of data there. Travel habit of all Pakistani adult citizens. We could just take a sampling of the data sets to look at the travel habits. Okay, this is a good. You finish collecting data on a small study of the wing measurement of 10 butterflies. That's it. Combination on your decision for your not sampling. 10 butterfly is a small data set, so sampling isn't useful here. Because it's just 10 butterflies. You get the idea now. This is just 10 butterfly. This is not a good amount of data to do sampling from. So that's the answer there. So let's continue. Okay, so let's read this example. Simple sampling with pandas. Let me look at the data set that we have here. So we have access to the data set that we're using for this lesson. I'll drop a link so you can download the data set for your practice purpose also. So simple sampling with pandas. Throughout this chapter, you'll be exploring song data from Spotify. Okay, we have access to that data set. Let me just connect to that data set really quick. I'll just use this my old method for now. Okay. But the song data is in a feather file. So I've never connected to a feather file before. So let's see. Let's do something real quick. Let's continue that for now. So each row of this population data set represents a song, and there are over 40,000 rows columns, 40,000 rooms. Columns include the song name, the artists who performed it, the release year, and the attribute of the song like its duration, tempo, and danceability. You start by looking at the durations. The first task is to sample the Spotify dataset and compare the mean duration of the population with the sample. Spotify population is available and finance is loaded as PD. So okay, sample 8,000 rows from the Spotify population, assign it to Spotify sample. Okay, let me connect the data set first. Okay, okay, when you're having a large data set, it's better to use further. Let's use the further file. So I'm going to use this same method to load the data sets. PD.read further, then the file paths. Okay, hold on a minute. Let's see if it's going to work. Oh, we have an error. Okay. Uh-oh, we have an error. Let's code an R here. Okay, we know it's there. So we are going to call these data sets Spotify. Spotify. Let's call on a Spotify data set and see what we have here. Voila. So we have our data set. You can see the acousticness of the data set, the artist, the danceability of the data set, the duration in milliseconds, duration in minutes, energy, explicit, the ID of the song, the instruments. It's quite a lot of data. Let's look at the shape of the data sets. So we know how many rows of data we are dealing with. Over 41,000 rows of data and 20 columns. Interesting. Okay, and let's move on. So this is asking us to get a sample of the data sets. It says sample 1,000 rows from Spotify. Okay, that would be so sample 1,000 rows from Spotify population, assigning it to Spotify sample. Could that would be Spotify population? Hmm. Okay, it says let's listen to the instruction. Sample 1,000 rows from Spotify population. Let's see. Okay, Spotify population dot sample. So the number of sample we want to do is 1,000. Let's run the code and see. And voila, we just did sampling for 1,000. You can see. You just pick 1,000 sample unique rows. You can say 1,000 rows by 20 column. Let's do the same thing here. Mm, so it's going to be Spotify sample. I want it to be Spotify dot sample. Then we pick 1,000 rows. So I call on Spotify sample now. We should see our results. You see now we have 1,000 rows. These are random rows from our data sets. Let's do dot edge. It will just show the first 5 rows there. Interesting. Okay. So calculate the mean duration in minutes from Spotify population using the pandas, using pandas. They calculate the mean duration in minutes from Spotify sample using pandas. Okay, we're going to calculate the mean from the main data set and the mean from the Spotify sample that we created. Okay. So mean duration sample. So that is going to be our Spotify population. The mean column, duration column. I'm going to select the duration column. Let me just double check the duration column in minutes. Duration column, there are two duration column. Is the duration column in minutes or in milliseconds? Hold up a minute. This is year the song was released, the valence, tempo, speechness, release dates. We have a couple of columns to work with here. Let me just go for duration. Let's see what they mean here. Mean duration of population with the sample. Okay, since they didn't specify, let's just pick on duration here. Duration. That's mean. Let's see. Then the next one is the Spotify sample. So let's run the code and see what we have here. Ooh. So I'm having an error on duration. Let's see. So it should be duration in minutes. Let's go for duration in minutes there. So let's do that again. And voila, we have our results here. So let's run this in this my Jupyter notebook also. Okay, so mine is Spotify. Then the next one is Spotify sample, which is this one here. That is correct. Now let's look at the mean, compare our results. And voila. So you can see the means are kind of similar for the whole population, which is the main data sets, and for the sampling one that we picked a couple of unique 1,000 rows of data here. When you compare the what we have here, you can see this 3.852 and 3.84. 3.852, then 3.824. They are quite similar. So let's move on. We are doing good. Fantastic. So simple sampling and calculating with NumPy. You can also use NumPy to calculate parameters or statistics from a list or pandas series. You will be turning it up to 11. You will be turning it up to 11 and looking at the loudness property of its song. Okay, you'll be tuning it up to 11 and looking at the loudness property of its song. So the file population is available and NumPy is loaded. Okay, create a pandas series loudness population by subsetting the loudness column from Spotify population. Oh, we need to subset for the loudness column. I want to pick on the loudness column only. Okay, so it's going to be Spotify. Spotify population. Then pick up on the loudness column. This will return only the loudness column, which is this column here. So we want to look at this column. Let's see. Great. So if I call on this loudness population, I should have only one column. You can see the loudness column, this column here, from this column alone. This is what we are seeing here. So I'm going to do dot head. Let's return the first 5 rows of that column. The data type is float data type. So we are doing great. The sample loudness population to get 100 random samples. Okay. Loudness pop. Dot sample. I want to sample just for 100 rows. Well, so we've sampled 100 rows of data here. Well, I just prefer to do it in a simpler manner. So I'll just so calculate the mean of Latin population using the term pi. So let's calculate their means. Okay, we want to calculate the mean of the Latin population. Mean loudness population. That will be loudness samp. Loudness samp dot mean. No, we want to do the loudness pop. So mistake there. So loudness population is getting kind of arousing. Loudness pop. Loudness pop dot mean. Then the loudness sample dot mean. So let's run the code and see. I'm sure our results. You can see they are quite so similar. Can get a little bit confusing as we try to do a lot of mathematics there. Let's do the same thing here. So we can see the mean loudness population, which is this initial pop here, loudness population that we did here. When we actually create the loudness population column, we're only subsetting for the loudness column. So this is it here. So if I run this line of code, I should have the same results here. Interesting. So we did a sampling from this actual loudness population here. Quite funny though, and straightforward. Okay. Devious means again. Notice that the calculated value, the mean, is close but not identical in each case. Exactly. They are quite close but not identical. Oh, I just ignore this. We've been learning quite a lot. Just skipping some this. This is some technical issue. So let's look at convenience sampling. Good. Oh, we're almost through with the lessons here. So there's something called convenience sampling and random sampling and pseudo-random sampling. I think convenience sampling is also called random sampling, and there's pseudo-random sampling. So let's look at those keywords.
The point estimates you calculated in the previous exercises were very close to the population parameters that they were based on. But is this always the case? In 1936, the point estimates you calculated in the previous exercises were very close to the population parameters that they were based on. But is this always the case? In 1936, a newspaper called the Literary Digest ran an extensive poll to try to predict the next US presidential election. They phoned 10 million voters and had over 2 million responses. About 1.3 million people said they would vote for Landon, and just under 1 million people said they would vote for Roosevelt. That is, Landon was predicted to get 57% of the vote, and Roosevelt was predicted to get 43% of the vote. Since the sample size was so large, it was presumed that this poll would be very accurate. However, in the election, Roosevelt won by a landslide with 62% of the vote. So what went wrong? Well, in 1936, telephones were a luxury, so the only people who had been contacted by the Literary Digest were relatively rich. The sample of voters was not representative of the whole population of voters, and so the poll suffered from sample bias. The data was collected by the easiest method, in this case, telephoning people. This is called convenience sampling, and is often prone to sample bias. Before sampling, we need to think about our data collection process to avoid biased results. Let's look at another example. While on vacation at Disneyland Paris, you start wondering about the mean age of French people. To get an answer, you ask 10 people stood nearby about their ages. Their mean age is 24.6 years old. Do you think this will be a good estimate of the mean age of all French citizens? On the left, you can see mean ages taken from the French census. Notice that the population has been gradually getting older as birth rates decrease and life expectancy increases. In 2015, the mean age was over 40, so our estimate of 24.6 is way off. The problem is that the family-friendly fun at Disneyland means that the sample ages weren't representative of the general population. There are generally more 8-year-olds than 80-year-olds riding roller coasters. Let's return to the coffee ratings dataset and look at the mean cut points population parameter. The mean is about 82. One form of convenience sampling would be to take the first 10 rows rather than the random rows we saw in the previous video. We can take the first 10 rows with the pandas head method. The mean cut points from this sample is higher at 89. The discrepancy suggests that coffees with higher cut points appear near the start of the dataset. Again, the convenience sample isn't representative of the whole population. Histograms are a great way to visualize the selection bias. We can create a histogram of the total cut points from the population, which contains values ranging from around 59 to around 91. The numpy.arrange function can be used to create bins of width 2 from 59 to 91. Recall that the stop value in numpy.arrange is exclusive, so we specify 93, not 91. Here's the same code to generate a histogram for the convenience sample. Comparing the two histograms, it is clear that the distribution of the sample is not the same as the population. All of the sample values are on the right-hand side of the plot. This time, we'll compare the total cut points distribution of the population with a random sample of 10 coffees. Notice how the shape of the distributions is more closely aligned when random sampling is used. Let's plot some histograms.
Okay, let's plot some histogram. So our findings from the sample generalizable. We just saw how convenient sampling, collecting data using the easiest method, can result in samples that are representative of the whole population. Equivalently, this means findings from the sample are not generalizable to the population. Visualizing the distributions of the population on the sample can help determine whether or not the sample is representative of the population. So the Spotify dataset contains an acousticsness column, which is a confidence measure from 0 to 1 of whether the track was made with instruments that are plugged in. You compare the acousticsness distribution of the total population of songs with a sample of the songs. Okay, now let's do that. So plot a histogram of the accoustiveness from Spotify population with beans or with 0.11 from 0 to 1 using pandas dot ist. Okay. Okay, let's do that. Hold on a minute. I want to do it here first. Voila. So see what we have here. Dot ist beans equals to 100. Okay. So we don't want 100 beans. We just want a little bit of population. Let's connect like this. Hmm. Let's stick to this first and just say, and let us just copy this line of code and make use of it here. Oh, this should be Spotify population. So voila. So we have the same result. So beans plot histogram with a consistent from Spotify population with beans bits of 0.011 from 0 to 1 using pandas dot ist. So did you use np.range to write the beans of width 0.1? So I was supposed to use the np.range method. Okay. Spotify population, the acoustics column dot ist. Okay, I was supposed to use the, let's use the np.range, np.range will now be equal to, so the stop value is exclusive. 0, 1, then 0.01. Okay, so let's see what we have here. Oh, there was 1.0. Is this a 1.01 and 0.01? Oh, let's see why we are getting this error. Beans. Oh, I didn't mention the beans keyword there. Is beans.np.arange 1.01. Ah, voila. So that is correct now. So let's see it in action here. Ah, voila. So you can see the difference. So 0 to 1, 1.01, then to 0.01. Interesting. So update the Instagram code to use the Spotify mysterious sample data sets. Oh, what is that? Do we have that? We don't have that here. There's a mysterious sample data set also. Oh, okay. Let's see this. Call it the mysterious sample data set. Look at this one here. Just coming to this side. So compare the two histograms you drew. Are their consistent values in the sample generalizable to the general population? Oh, that's not possible. When you look at this is on the left hand side and this is on the right hand side. Hmm. Oh, hold up a minute. Hold up. That's it. So the consistence analysis, their consistence values in the sample are all greater than 0.95, whereas they range from 0 to 1 in the whole population. You see that they range from 0 to 1, 0 to 1, 0.00, 0.02 to 1 in the general population, while in this mysterious, they are both 0.95, you can see 0.95 here. So are these findings generalizable? I doubt that. So plot a histogram of duration minutes from Spotify population with the beans of width 0.05 from 0 to 15 using the pandas is okay. Let's do the same thing here. I'll just copy this line of code here and say Spotify duration. Hold up minutes. So we only need this beans line of code. The beans. Now the beans dot np dot n should start from with bean width of with bean width of 0.05. So this is how the bean width should be. Should be that long 0.05 from 0 to 15. 0 to 15. So from 0 to 15. So this should be 15. Let's on the code and see. Oh, we're having an error. Oh, voila. So this is the highest range is 15. We start from the highest. The event should be 0.05. Let's see. Voila. 0 to 15. But the event should be 0.05. Mm. I use 0 points instead of 0.05. You see, so the event should be 0.05. 0. This is how it's supposed to look like. 0.0. Let's see. Oh, okay, let's see the mistake we are making there. 15 points. Oh, since the difference is 0 points, being width of 0.05, the difference will be 0.5. Okay. So I'm looking at the difference. Since it's 0.5, so I'm going to add it to this. Will be 15.05. 3.5. Just adding 15 to 0.5. So the difference will be 2 points. So update histogram code to use the Spotify mysterious sample data set too. Let's make use of this sample data set too. On the code. Now let's answer the same question again. Hold up. Let's look at the main sample. Oh, they are almost the same thing. So this is the general population, and this is the sample population. So no, no. Hold up. Okay, any sample. So then the sample should work then. validation distribution there. So the sample selected. Okay, since they have the same bell curve shape, so the results are the same thing. So this is the random, this is the general population, and this is the random sample selected. So they gave the same result. Oops, time is going. Okay, let's quickly finish this. We're on the last, what is called pseudo-random number generation. So let's see what that looks like.
You previously saw how to use a random sample to get results similar to those in the population. But how does a computer actually do this random sampling? There are several meanings of random in English. This definition from Oxford Languages is the most interesting for us. If we want to choose data points at random from a population, we shouldn't be able to predict which data points would be selected ahead of time in some systematic way. To generate truly random numbers, we typically have to use a physical process, like flipping coins or rolling dice. The Hotbit service generates numbers from radioactive decay, and random.org generates numbers from atmospheric noise, which are radio signals generated by lightning. Unfortunately, these processes are fairly slow and expensive for generating random numbers. For most use cases, pseudo-random number generation is better, since it is cheap and fast. Pseudo-random means that although each value appears to be random, it is actually calculated from the previous random number. Since you have to start the calculation somewhere, the first random number is calculated from what is known as a seed value. The word random is in quotes to emphasize that this process isn't really random. If we start from a particular seed value, all future numbers will be the same. For example, suppose we have a function to generate pseudo-random values called calcNextRandom. To begin, we pick a seed number, in this case, 1. calcNextRandom does some calculations and returns 3. We then feed 3 into calcNextRandom and it does the same set of calculations and returns 2. And if we keep feeding in the last number, it will return something apparently random. Although the process is deterministic, the trick to a random number generator is to make it look like the values are random. NumPy has many functions for generating random numbers from statistical distributions. To use each of these, make sure to prepend each function name with numpy.random or np.random. Some of them, like .uniform and .normal, may be familiar. Others have more niche applications. Let's generate some pseudo-random numbers. The first arguments to each random number function specify distribution parameters. The size argument specifies how many numbers to generate, in this case, 5,000. We've chosen the beta distribution, and its parameters are named A and B. These random numbers come from a continuous distribution, so a great way to visualize them is with a histogram. Here, because the numbers were generated from the beta distribution, all the values are between 0 and 1. To set a random seed with NumPy, we use the .random.seed method. Random.seed takes an integer for the seed number, which can be any number you like. .normal generates pseudo-random numbers from the normal distribution. The loc and scale arguments set the mean and standard deviation of the distribution, and the size argument determines how many random numbers from that distribution will be returned. If we call .normal a second time, we get 2 different random numbers. If we reset the seed by calling random.seed with the same seed number, then call .normal again, we get the same numbers as before. This makes our code reproducible. Now let's try a different seed. This time, calling .normal generates different numbers. Let's sow some random seeds.
Oh, that's a lot of random technique there. So let's give it a shot. Creating random numbers. and understanding random seeds. Oops. We have 4 steps here. Generate 500 random numbers from a uniform distribution, setting the parameters low to -3 and high to 3. Okay, let's see. So I'm going to use the uniforms, generate random numbers from uniform -3 to 3. You've used the sample to generate pseudo-random numbers from a set of values in a data frame. A related task is to generate random numbers that follow a statistical distribution, like uniform distribution or a normal distribution. Each random number generation function has distribution-specific arguments and an argument for specifying the number of random numbers to generate. Oh, a lot of technical keywords. Let's see. Generate random numbers from a uniform -3 to 3. np.random uniform. Okay, let's see. Let me do it in my Jupyter notebook here. Okay. Oh, you can see the random numbers. Interesting. So np.random uniform low -3 3. Size is 500. Okay. We have almost same similar random numbers there. They are quite similar, but they are also absolutely random. Let's submit that. Generate 500 random numbers from a normal distribution, setting the parameters log to 5 and scale to 2. From a normal, what do I mean by normal distribution? So the log is going to be log scale size. Okay, that's how straightforward it is. Then plot a histogram of the uniforms with bin width of 0 to 5 from -3 to 3 using the plus is. Hmm. So PLT.E, so it's going to be uniform. So our bins is going to be the head pin range. Oh, I'm missing. Which be uniforms. Oh, I see the bins of the random number. So PLT.is uniforms. Where is uniform? The uniform, the bins that arrange plot histogram of uniform value bin weight of 0.25. This is what it means here. Voila. And there we have it. So if I should change this is supposed to change based on the random numbers. It's still the same thing from 0.25 to minus 3 to 3.25. Okay. So plot a histogram of normals with bin width of. Okay, let's do the bin width for normals. It's going to be PLT dot normals. So it's going to be normals. Normals. So from 0 minus 2 to 13, width of 0.5. So minus 2 to 13.25. Will that be 13.5? Voila. This is quite close to a bell curve histogram. That's what we have here. Voila. This is like a bell curve shape histogram. So these are those random numbers. This visualization you're seeing here, the random number that we generated from this line of code here called np.randoms. We scale the log to 5, the scale to 2, and the size of random numbers to generate to 5,000 rows of numbers. Interesting. Okay, dokie histogramming. Okay, the final one that says understanding random seeds. Oh, hold up, let me check something there. See, I saw something here. Okay, dokie. Notice how the histograms almost take the flat and bell curve shape of the uniform and normal distribution, but there's a little bit of random noise. Exactly. You see a lot of random noise there. So which statement about x and y is true? So why random numbers are important for many analysis? They create a problem. The results you get can vary slightly. This can cause awkward conversion. It can cause what is called awkward conversions with your boss when you script for calculating the sales forecast, giving you different answers this time. Setting the seed for non-prime random number generator helps avoid such problems by making the random number generation reproducible. So which statement about x and y is true? Import random.seed x np.random normal size 5 y. Okay, so let's see. We have y np.random. So x and y have identical values. The first y values of x is identical to the first value of y, but other values are different. The values of x are different from those of y. What's the option? Values are different from those of y. Hmm. If you say x and y have identical values, the arrays are entirely different because the first value of x is identical to the first value of y, but other values are different. That should be false. Let's go for this last one. X and y contain same code and both appear directly after the other has been set to the same value. Ooh. Each random number is generated deterministically from the previous random number. So the first number being the same will mean the following numbers were the same too. So the first value of y have identical values. Oh. So I need to run the code. Okay. Let's run the code. Oh, it's not running though. And the last option should be the answer. Exactly, correct. Since different seeds are used, the generation will be different from x to y. Because different seeds are actually used here. We look at the seed here. Let's take a little look. Oh, MP random seed is 456, seed is 123. So the values on x are different from those of y. So different seeds were used. Oh, voila. So we completed this answer on random sampling. Okay. All right. I think my camera just took another turn right there. But that'll be the live stream for today. So if you find value in this learning journey with me, do well to support the channel by giving the video a thumbs up, hit that subscribe button. And I'll see you on day 73 as we continue our learning journey of Python. Voila. Bye for now. I need to troubleshoot my camera real quick. So, but it's great seeing at the end of the lesson. So I'll see you on the next lesson, which is sampling methods. We'll be looking at the different sampling method. It's time to get our hands on and perform the 4 random sampling method. In fact, which is simple, systematic, stratified, and cluster sampling. Okay, looking forward to that. I'll see you tomorrow, day 73.